We are in a micro city in EPFL Neuchâtel, such that all the speakers can be in the same room, so to facilitate the meeting. I will do a short introduction first, and I would like to welcome all the attendees for this IEEE Stamm meeting about photovoltaics. You probably all know the IEEE, Institute of Electrical and Electronics Engineers, with 423,000 members in 160 countries around the world. But you may wonder, what is this Stamm? In German-speaking places, the Stammtisch is typically a table in a cafe or restaurant where people meet to regularly exchange ideas, opinions, and more. Hugo Wies, here present, the chair of the IEEE Life Member Activity Group of Switzerland, launched this idea of the Stamm to take place every last Monday of the month at the EPFL Lausanne in the Palace Auditorium in collaboration with the IEEE student branch of EPFL. Last year, with the virus situation, we had to suspend our gatherings, but a month ago we resumed with a well-attended online meeting about amateur radio, and we hope to be able to resume the on-site meeting in end of June. Hugo is organizing something about the history of semiconductor technology. As you know, the motto, and it's shown on the slide at the bottom, of the IEEE is advancing technology for humanity. The theme of today's meeting on photovoltaics is well aligned with this goal. While people share on social media their fear about technology, it is our role as engineers, citizens, or decision makers to promote technology advances that are good for humanity. And if you are not a member of the IEEE, I propose you to join. Then you can contribute not only on technical topics, but also ethical, educational, and historical subjects. I will now introduce the first speaker. Michel Villoz graduated in 1977 from EPFL, École Polytechnique Fédérale de Lausanne, with a diploma in electrical engineering. In 1980, he joined the world of solar energy to coordinate the technology transfer to Switzerland of a solar cells production line from SolarX USA. He then managed the production of cells and participated to the design of the Pazan Sun Simulator. Today, he works mainly as an independent consultant and expert in photovoltaic engineering. Furthermore, he provides in-house PV training at PVsyst and on-demand specialized training in PV technology abroad. Michel is the author, with Anne Labouret, of a Solar Voltaics published by the IEEE Stevenage UK, and of Construire Écolo, published by Duno in Paris. Thank you, Michel, for presenting. So I let you switch to the presentation mode, if you can.
Okay. Thank you, Michel. As you know, we will speak of photovoltaic devices. And the first information we need to know is, what do we get from the sun? You know that the sun is sending us the light, which can be described as a wave, and photons. You have two descriptions that were first described and defined by Einstein. And here we see the spectrum received. And this AM information is the quantity of atmosphere. So AM 0, it's outside of the atmosphere. And AM 1.5 is a kind of light we use to test solar modules. And if you look in this, you see this, the visible spectrum from 0.4 to 0.8. And the rest is extra heat at right and high energy light at left. The PV conversion, it's photons that can come inside a material. And we use most of the time silicon. And each photon can with change, relays electrons and create holes. So we speak of electron holes pairs. That means that the electron will go from the valence band to the conduction band and be available to carry any current. In crystalline silicon, we need an energy higher than 1.1 electron volt, which corresponds to 1.13 microns, so in the close infrared. In amorphous silicon, it is a bit higher, with 177 electron volts, which is related to this 0.7 microns wavelengths in the red. It's the main reason why we were using amorphous cells to power devices inside rooms, because they have a better efficiency in the blue. And you know that artificial lights, most of the time, don't have much red part in their spectrum. If we use silicon, we might, if we have those photons coming inside the crystal, they will change the resistivity. If we want to do something active, we have to push them. To push them, we will dope the crystal, adding foreign materials to polarize and create an electrical field. So silicon has two neighbors that would be okay, but in fact, we don't use the aluminum directly. We will use the upper neighbor, boron, most of the time with silicon, which will be the basis material. Then on the surface of this basis material, we will add phosphorus, which will create this electrical field between P and N region. If we look at an old cell, this was a cell built 40 years ago, but which has been fabricated for at least 30 years, I would say. If we look at what we have this wafer, which is doped with P, I said with boron most of the time. And this was probably chosen because in the 80s, the majority of wafers were P. Yes. So it was used for electronics. So at that time, we were following electronics, and the material were from microelectronics. Today, microelectronics could follow solar because the quantities are completely different. Now we have at least 50 to 100 times more wafers for solar than for microelectronics. But okay, at the time it was this. And if you look at the different layers, you see those small triangle means that we have on the surface, we do some etching to produce small pyramids in order to collect light in many directions, not to have something flat, because the index of refraction of silicon is high. So we have first the triangle, those small pyramids, plus we put an oxide on top, which is a number 2 in this layer, which has an index of refraction roughly of 2, and the encapsulation is 1.5, plus the glass also 1.5. So we have different layers with different index of refraction to try to catch a maximum of light in any direction. Number 1 is the front grid. It's the little lines that you see on most of the cells. It's a mix of silver. This is important because the price of silver in the silicon today is number 2 in terms of cost of sale, besides the wafer. This N substrate, or just the N layer, will fabricate this electrical field between the N and P region. So it's really a shallow junction, very close to the surface. So when you do the metallization, it's better not to cross everything. And on the back, we call this the cell BSF because it is made of a P plus region with good contacts with aluminum. So on the front, behind the cells, there was a complete layer of aluminum, and there was a little field, P plus to P on the back. It was, we call this back surface field. And then there is a layer of aluminum, solderable metallization to put the cell in series. So this PN junction is a diode that you know probably. And in dark when you don't put any light, you have a typical curve of a diode. But to have an active element, then you put light on that diode and you get a current which can be extracted from the diode. And we have typical values. Open voltage means that we don't connect anything. That means that the photovoltaic current will be consumed by the diode. So if you look in infrared, an open voltage cell compared to a short circuit cell, it will be warmer because there is some internal dissipation. On the left, you have the short circuit current, which is an image of the quality of the cell plus the size. So why, if you make a bigger cell, you'll have more current, which is easy to understand. A typical module is made of, in this example, it's an old module which had 36 cells, enough voltage to charge a 12-volt battery. So this has been made for decades. And the typical 50-watt, roughly, module had an efficiency between 12 and 13%. If we want to do a system, we will use now a software to calculate how much energy we could produce. So I take a small example in the Swiss Alps, just to show you the importance of the environment. When we have mountains, it's always interesting to see what we can do and how much it is and how much we lose because of shading from the mountain. So I took an example in Le Cepé, in the Vaudoise Alps. And if you do a simulation, you have to know the location, then the tilt and orientation of the roof. You will draw how many modules you can put on that roof. You import your irradiance from a good database. You choose a module and an inverter, and you put typical value for losses. Then you get the horizon, especially in Switzerland, almost always, and you calculate the simulation. If necessary, you can draw a 3D layout to calculate shading losses, local losses. This is the screen where you choose elements. So in this example, I took a module from the biggest manufacturer today, the biggest Chinese manufacturer, Longhi, a typical module today, 370 watt for a 60 cell module. And I took an inverter from Austria, which is also very well known. And in this example, 6 kilowatt inverter. And here we see immediately a little calculation where we display the DC-AC ratio. And here we have 123, which might produce a small saturation loss because we have 6 kilowatt of inverter for 7.4 kilowatt of modules. Here we can also display a typical IV curve on top. So it's always interesting to know where we are and how we can, what our inverter can do. It can work from roughly 150 volts up to 1000. But what we are interested to know is what we call the VMP and the max peak power tracker in order to remain on that curve and to be at the knee at the best level of voltage and current and max power. Down you see where you fabricate, at what power you fabricate energy. If I take an example at 3 kilowatt, for example, here I have 300 something kilowatt hours built at 3 kilowatt. So it gives you an idea where we have what kind of type of energy. If I was in the south, I would have a higher density at right, and if I was in Stockholm, I would have a bigger volume at left. This is the horizon that we can get automatically. So you see that there is a big influence. And when we do the simulation, we have the results. And here the main information is that little value on top right, which gives 1229 kilowatt hour per kilowatt peak. So at this location, my system produced roughly 1229 peak hours during the year. In this program, we have a loss diagram, which allows us to immediately see if we can win something. So with a house, it's very difficult. You cannot change much. You can change modules. You can change the inverter to have other components, but you cannot change the tilt. You cannot change the azimuth because everything is fixed. You have already the building built. So we see in this range, this plus 11% first value is a gain because of the tilt and azimuth. Then we have a loss coming from the far shadings, the horizon. Then we have a IM. IM, it's a behavior of the module at grazing light. When the sun sets at the end of the day, there will be a time where your solar module will become a mirror. So you have a minimal angle, and then you have the energy cannot come inside the module. Then we have, this is purely optical, that first part. Then we have all the behaviors, which are typical values and losses. I have another example. If I do a small system on a building from a small factory, so it is a terrace in La Chaux-de-Fonds. Here we do domes. That means to have a high density of module, we have module looking east and west, if possible, or just following the building. In that case, it's not exactly east-west, it's northeast and southwest, but it's not the main thing. It's interesting to put a peak power, and with cheap module, especially in Switzerland, where the labor cost is high, it's better to put the maximum number of module for a certain project. Here again, I have the horizon. The choice of components. I'm using a module that was available last year. We did this at the end of last year. GA Solar, it's also a big manufacturer from China. And then ABB, it's inverter produced in Italy. Since this, they have sold the company to another group called FIMA. So ABB is not anymore the owner of that company. Here we have again the IV curve plus the density of energy depending on the power. Inside the program, we do a 3D design to be able to calculate the shading losses. And when we do the system, again, we have all the curves and production, and again, the losses. And so what is new here, we see that the first gain coming from the tilt and the azimuth is negative, because in dome, we have only 10 degrees of tilt, and we don't look with all the module looking south. Far shading is less of a problem than in the Alps. Then the near shadings, it's a loss because of obstacles of the building very close to the field. And IEM again, on this module is not so good. Then we have an extra shading loss, which is shadings electrical loss. This comes from the series connection of module. So maybe you have heard that on module you can put optimizers. That means that you can change something in the module to have a DC-DC connection just for each module. In that case, we could reduce this electrical loss here. We can win 30–40% easily. But it means that you add sophisticated electronic equipment on each module. If you think we have the temperature between, can be minus, slightly minus. In La Chaux-de-Fonds, we can have -10 for the module in winter. And in summer, we can go to 60 degrees. So if you think that you can put sophisticated electronic at those temperatures for 30 years without problems, you might choose it, besides the fact that it is expensive. But then you can have on your telephone the value of each module. This is fantastic information. But okay, we have clients asking for this. Myself, I refuse to do this when I have a roof difficult to access, because just going to the roof is more expensive than the product itself. So it might have a guarantee of 20 years, I don't mind. If just to go there I need a nacelle, you know, those things, a big truck. This is not impossible. This is a picture of that roof.
With the shades.
Well, yeah, I took this in December, just before the snow. So in La Chaux-de-Fonds, there is no miracle, you know. This year we had at least 70–80% loss in December. Oh yeah, at least, and January, February also. I have another. What do we do when we have finished the system? Today, what is good? Often we have a direct access to the web to the performance of the system. We did this in an upper valley, which is the Vallée de la Seine, when we have 5 buildings with exactly the same system, and then we can compare. So for the follow-up, it's very convenient because if one system is lower than its neighbors, we say, oh, there might be a problem, we can have a look and go up on the terrace and see what's happening. We get this kind of curve. So it's dome again. So you see 2 strings which have different behaviors because one is a bit better in the morning and the other one better in the afternoon. You know, it's normal because they don't look in the same direction. They're 180 degrees difference. And we have the total. So I have here 2 inverters, but I have 5 curves like that I can compare and see if one is much better than the other, just for following. And we can also look overall with many years. Here I have an example with 3 years, and we see that at the end of this month we have good results. And the last value, May 30, was fantastic. No clouds at all. So it's a very good day, the best day of May. But in 2019, May was much better in this example. What can we do when we have a simulator? We can also, on small system, we will not put instruments. It's too expensive. So if you have a personal system, you could say, okay, how can I control that my system is not aging? So one way is to do what we call a clear sky simulation. So we decide to make a simulation with days like that. So this is 2 days ago. No, this is yesterday. You know, last Sunday was bright, no clouds, and you get this kind of curve. It is not exactly symmetrical because my system looks in the direction of west. You see, it's a bit on the angle because of this orientation. So the azimuth is west in this example. And if I do a simulation with this light for the whole year, I can compare different years in the same month, for example. So if here I have an example, 2018, 19, 20, and 21 in May, and I take the best of this period, just to see if my system is aging. So in this example, I have 8% difference in 2018, then 8.9, then 9.1, then 8.9. So I can say from this that I don't have any real aging of the system. I have an example, the same kind of system, but we're not using this. I have a system near Fribourg, which has normal, I have 15 years of production, and the best year was last year. 2020 was fantastic. But everywhere, in the whole Switzerland, you know, was the best year because people were at home, I don't know. But there was more sun last year than any year of those last 15 years. So if we have normal system, standard simulation, I can compare years. So I took the same small system here, 2018, 19, 20. But with this, I cannot see if my system is aging because the climate is changing.
Yeah.
So it's just to see, okay, my system still works. And in this particular example, the best is 2020, but I knew it already. But I think it's a clear sky. I have used this for expertise to tell people you should clean. Because at distance, if you have access to daily values, you produce this list I had a big system. It was more than 5,000 modules on a big roof in Valais. And they were just asking, should we clean? In 3 years, they had lost 15%. But we didn't know. They had put sensors, but they never cleaned them. So it's a bit ridiculous situation. But with a clear sky, I was able to see, oh, when the system is brand new, I have a certain value between my simulation and my clear sky. Okay. Then 1 year after, and so on. And I had roughly 5% per year. It was also module at 10 degrees tilt. So even in Switzerland, if you don't have a strong tilt, a big tilt, it makes sense to clean. No. It's not only for, this winter, we had this rain from the desert. Mm-hmm. So in some place, if you do a design in the Middle East, the cleaning is one main issue. Start before doing anything. You have to say, okay, we will clean that way, we will choose this robot. Because I was a few years ago in Khartoum, and we had an atmosphere brown every day. And I've seen the same in Baghdad a long time ago, where we had everything. We had a fridge and modules. In 1 day, the modules were completely brown. So here, you don't have, you have to choose. You cannot choose, you have to clean. I don't know if you have questions. Maybe we'll do this at the end.
Yeah, I was thinking of doing all the questions at the end. Yeah,
mm-hmm. Okay. So then, if not the case, I give my connection to Professor Ballif.
Okay, you can listen. Okay, fantastic. Fantastic. And you can see my screen as well.
Yes.
Yes.
We see you.
Okay, perfect.
We see you.
So it will be a pleasure in the next half hour to try to go through a journey. We have seen what is a PV power plant. We have seen some of the energy analysis in this PV power plant. And now we will really try to go a big travel around what happens in this world of photovoltaic. And as a start, I just want to remind you that our goal of using solar energy is twofold. First of all, we would like to create an energy system that is less costly in the future. And we think that it is possible to do that in large part thanks to photovoltaic. And second, we want at a global level, we would like to really mitigate global warming. And the question is whether photovoltaics really has this capacity or not. And we're going to check some of the numbers, including in some of the numbers with respect to the gray energy. So first of all, what you need to know is that there's been this huge increase in the production capacity accompanied by a strong decrease in the price of the photovoltaic modules. As you've heard, we roughly sell modules according to a unit which is called the watt, which is the maximum power given under one sun. And this watt has come very much down in terms of pricing. At the beginning of the year, it was something like 20 to 22 cents per watt. Now it went up again a little because there is too much demand for photovoltaics and there is some shortage in the refinery of polysilicon. But this price in the long term will continue to go down. So we're talking today about getting photovoltaics module for something such as around 50 Swiss francs per square meter. And this module will produce in Switzerland over its lifetime around 6,000 kilowatt hours at least. So you can quickly make the calculation in your head and you'll find out that just a part of the module in Switzerland, even if you import the module, is less than 1 cent per kilowatt hour of electricity. And it is interesting because you can make the same calculation. Should I import photovoltaic modules or should I import oil? And when you make the calculation, you find that it is a factor 15 more expensive in terms of energy to import oil than to import a photovoltaic module. So the economics is quite quick in terms of, let's say, import. With a photovoltaic system, you will have cost at installing in Switzerland, but this cost cannot be, let's say, spent at any other places than in Switzerland. You cannot, hire Chinese people to work on a roof. You cannot hire people from Saudi Arabia to install the photovoltaic system. So from, let's say, macroeconomic perspective, photovoltaic is really a good option thanks to this lowering in the price of the photovoltaics module. If you look at the full system and you go to sunny countries, they're starting to build larger and larger power plants. And you can see now these very low prices for bids for solar electricity that are given in price range below 2 cents per kilowatt hour, which makes, and this is quite new because 5 years ago it was not yet the case, but it makes that photovoltaics is really cheap in these sunny countries, and not only cheap, it is a factor 3 cheaper than any other, let's say, kind of electricity generation. Is it fossil? Is it nuclear? Is it even a gas power plant? So it has become very cheap, and this opens a lot of perspective. In Germany, you are at around twice the price. That means more 4 cents for the large power plant. And in Switzerland, certainly you can also do electricity, depending on the size of your system, between 5 cents and 20 cents if you make a very small rooftop system. And what is the problem we're trying to solve? It is this problem, and I like to show this graphic here. It shows the quantity of primary energy that we use annually. And we're talking about a huge quantity, mostly based on fossil fuels, coal, oil, and natural gas, and with a small share here of hydroelectricity, nuclear energy, and the new renewables. And what you can see is that basically nuclear is not growing much. Hydro, we have exploited much of the capacity. And the problem we are facing in terms of mankind is to replace this in gray, red, and green with this new renewable energy. Of course, you can still try to develop nuclear, but you'll see the numbers. You need to put 10,000 more nuclear power plants, so it might not be the ideal option to really try to get rid of the fossil fuel. But this is a challenge that we are trying to do. And you can also have a look at the magnitudes, orders of magnitude, 162,000 terawatt hours, and it shows you how many wind turbines and, let's say, solar systems you should install to make this the same amount of useful electricity. In this graphic of BP here, you are considering a factor 2.5 more energy for the clean electricity to take into account the low efficiency of the, let's say, all the power plants or motors working on fossil fuels. But anyway, so this is the order of magnitude of things we need to replace. And we see, and this is even worse, that this is always increasing. We've not been able to reduce our primary energy consumption, and except maybe just during the short COVID time, but it's going up again. And this is, of course, accompanied by an increase in the Earth's population. You can see here the rate of increase of the world population. So fortunately, the population should stabilize around 2,100. But what you see is that even if people wanted to restart to reduce their consumption, we likely need still quite a lot of energy. If we could use twice less energy because we change our way of living, that would be fantastic. But it's not going to be easy to implement that. And even then, we still need to reduce strongly our fossil fuel energy consumption. And the first question is technically, would it be possible to really substitute all this fossil fuel? And the answer that you find, and I'll give just a few answers here, is that yes, it is possible. And you need to consider some large system to do that. For instance, you can have a look at the study of the group of Breyer, who is replacing in Europe all the electricity from coal and gas and even nuclear with wind and photovoltaics and a small part of biomass. And this is in a scenario where there is a moderate growth of electricity demand, so it's not yet the full scenario. And they find, very interestingly, that it is possible to balance every hour of the year between solar and wind at the European level. They also find that you need either to re-enhance some connection between some part of Europe, or that you need to use a little more storage. But storage here, you don't even need long-term storage. You need mostly short-term storage. In this short-term storage will come either from hydro, we already have a big part of it, or it will come from batteries. And this can be either prosumers, people who have a battery at home, or it can be the battery of cars, because, of course, in all this scenario, most of the cars go to electric from combustion motors, and most of the heating system go also towards heat pump solution. And you can do the same scenario at the world level, and you find two things. First of all, you find that typically you will need to put quite a lot of solar and wind, typically 30 or 40 terawatt, 40,000 gigawatt. So it's quite a lot of solar panels. But the second thing, even when you make this scenario, is that you find that your electricity, for instance, in Europe, would be cheaper than what we have now. So it will be cheaper, it is doable, but of course, these are not the same people who are winning and losing. And the question would be, of course, is it also cleaner? You can find more global scenarios for Europe. You can see this study of Solar Power Europe, also validated by the Lund University, where they also introduce some role for the hydrogen, which is important if you want to also clean up some industrial processes, steel preparation, metallurgical processes. You have a scenario that has been proposed by Roger Norman for Switzerland, where you also show how you need to develop solar. You would need ideally to have also wind in Switzerland. It's good for the winter time. If we have not enough wind, we'll have a deficit more in winter, which we can either compensate by having a few gas power plants or by importing hydrogen or by importing electricity. But even in the worst case, we would still be able to decrease our CO2 emission by up to 86% while still keeping gas for 1 month or 2 months in wintertime. So anyway, the orders of magnitude are the same everywhere. In the case of Switzerland, it would be between 35 and 50 gigawatt of photovoltaics, which we need to install. Today, we have only around 3 gigawatt. So we still need to multiply by a factor, let's say 15, what we have installed in PV in Switzerland. But if you are serious in a general way, there are not so many other options than developing massively this renewable energy. And in the case of Switzerland, we should also cover a large fraction of our roofs. People who install a small fraction of the roof are wrong. This is an unsocial and unecological act. You should put as much PV. We need to put as much PV if we want to keep coal and gas out. And I come back to that point. But you have understood we need a lot of solar. What does it mean practically? It means that we should still increase by a factor 8 to 10 the annual module production, going towards, say, 1 terawatt or 1.5 terawatt annually. We are around 160 gigawatt for this year. Of course, most of the scenario you read from many agencies, they're always wrong and they don't capture the dynamic that it could be possible to have here. And it's interesting to just evaluate. If I wanted to install enough production capacity to refine silicon, to make the solar cell, to make the solar modules, how much would I need to invest? Well, it's quite easy. You can calculate based on the cost of each equipment from Stamm to modules, and you find that you should invest around $18 billion per year over 10 years. You invest that, and that it's nothing. It's nothing. 18 billion. It's I can give you a lot of examples. It's $180 billion. And with that, you would have all the manufacturing capacity for the PV modules you need worldwide, including for refining all the raw materials and so on. So it's not a problem. This is what I call peanuts. Of course, you just need to have the will to do that. But it also means one thing, and it's very good because I'm working in the field of innovation in solar, is that there is still a lot of room for developing new things. We need better photovoltaics. We want to improve every aspect of it because it makes the energy transition easier. And of course, we have this technology evolution. And we've seen that you had this first aluminum back surface with solar cells. And for people who follow the market, they've seen that the module power is increasing almost every year. So there are technological improvements. And I will just show you a few of them. And I will also show you a few of the things that we do in Neuchâtel, because you have more than 100 people working in Neuchâtel at EPFL and at the Swiss Center for Electronics and Microengineering, CSEM, working at developing this technology of the future, or of today, actually. And the first point is first to really analyze this curve, which is the average module efficiency that you can buy on the market. Not the best, but the average module efficiency. So the market, to be clear, is 95% crystalline silicon, and 5% is maybe cadmium telluride, and 0.1% are other technologies, but it's mostly crystalline silicon. And what you can see is that there is every year an average improvement of the module of around 0.4%. And it means that if you develop something and you want to enter the market, and the big market in 2025, you should have modules that at least will have 21 to 22% average efficiency in 2025. Otherwise, don't think of entering a mass market. And for 2035, this will be 24 to 26% module. And what is making this improvement possible? There are two things that are making them possible. One is the continuous improvement of each technology. And the second one is the massive industrialization. The higher the volume, the more you're able to decrease also the cost and to improve step by step the technology. And sometimes you have technological changes. So you don't need to remember all these pictures, but this gives you a nice overview of many of the kind of solar cells that are on the market, such as this was the old solar cell, the first one that you can see on top here. This is a new one, which is taking now more and more space on the market. This is called the PERC solar cells. And soon you will see more and more top-con solar cells. You will see more and more heterojunction and sometimes back-contacted solar cell. And this technology, like such as the aluminum BSF, it was here for 10 years, 15 years, 20, but suddenly the PERC solar cell was made sure to enter the market. And in 3 years, the full market has shifted from this blue part, which were mostly multicrystalline or large-grain silicon made with this aluminum back surface with solar cell, to monocrystalline silicon made with the PERC technology. It flips very quickly. And some space available here in black for this new kind of solar cell, such as top-con heterojunction and others that I will shortly describe. And for instance, in Neuchâtel, one of the things we've been working very hard based on the expertise that was developed in the field of thin-film silicon and started well before I arrived in Neuchâtel by Professor Arvind Shah, who will speak after me. We have taken over the process that we use for the thin-film silicon to make, on top of crystalline silicon wafers, to deposit very thin layer of amorphous silicon, which allows you to have at the same time a fantastic surface passivation, no more recombination of carriers, but also at the same time, if you put a dopant on both sides to really collect the carriers, but without any metal touching the silicon. And this kind of solar cell have much higher voltage than other solar cells. They have 740 millivolt, which means that they have a better temperature coefficient, and that consequently they provide you even more energy per watt peak. And at EPFL and at CSEM, we can make large solar cells reaching something such as 24.2 up to 24.7%, which is better than the PERC solar cell. As some industry, we can really do many more samples than we can do, can reach close to 25% in R&D mode and over 24% in production. So heterojunction is one of the technology we developed, and it has been now marketed and developed and industrialized in many countries in Europe. And in particular, we work with the Swiss group Meyer Burger that have installed production line in Russia, that have installed at Enel in Italy, at REC in Singapore. But it was difficult to sell to Chinese company that wanted to have only specific sets of equipment. And Meyer Burger at some point decided to not sell production line, but to become a module manufacturers. So 1 year ago, they changed the strategy, and now they just inaugurated new production lines in Germany that should make module reaching close, but not exactly 22%, hopefully soon. One of the best module on the market and with a better temperature coefficient and made in Europe. Solar cells made in Europe, silicon made in Europe by Wacker, so the food chain in Europe. And both Enel and Meyer Burger have announced that they want to go to 7 gigawatt of production capacity of solar panels. So this is a kind of renaissance of the European industry. So this is for this heterojunction. And here, one point, you need silver, of course, but the uniqueness of the process of Meyer Burger is that they have an interconnection technology that uses much less silver than any others. And they think it's a unique selling point. And if you really want to get rid of silver, we have already prepared all the process made with copper plating. So we can also substitute silver with copper plating. It's just a little more complex. So if the silver price goes too high, we're ready to jump to specific process with copper plating. which is always very specific for silicon. And here you can see we could make a large solar cell with close to 24.7%. If you want to go further with silicon, you can do so. And one of the things we have patented, but also published in Nature Energy, was a special heterojunction solar cell where all the contacts are at the back. And we've certified more than 25% here. I think some industrial partners have certified 25.4%. We also reached some such results in the lab. So very promising technology based on heterojunction, but I cannot say anything anymore about that. You'll find out hopefully in a couple of years why. So now you all ask yourself, fantastic, but is it really sustainable to work with photovoltaics? And of course, I hear a lot of things about all the bad things, such as you cannot make solar panel without destroying the environment. And there are a few points to pay attention. The first all is, of course, you need some raw material. Well, you need sand, but we have so much sand, and it's certainly not photovoltaics which will destroy the sand reserve. We need some rare materials such as silver, in some cases such as indium. We can substitute them with other materials. There is no problem. Silver could be substituted with copper, and there's still quite a lot of silver. Of course, all the mining, as for every field, should apply good practice. This is not specific to photovoltaic. But there is relatively little issue with that with photovoltaics. Now, one issue is about the embedded energy, the CO2 content. And if you have a look at the old modules, of course, it was using quite a lot of silicon, and purifying the silicon was an energy-intensive process. But things have strongly evolved. And for instance, if you have a look at this reactor here, it is a reactor called a Siemens reactor, where you actually inject a cleaned gas of silicon trichlorosilane, and it will recrystallize along with filaments. And this is very energy intensive. And this is a way to get really pure silicon in the forms of chunks of silicon. And in this process, you will grow silicon, and then you end up with this kind of rods of silicon. And it used to be more than 200 kilowatt-hour per kilo to make 1 kilo of silicon. But thanks to the improvement in the much higher number of filaments, the length of the filament, they even have tubular filaments. They have reflected walls for these huge containers. They can make up to 10 tons of silicon at a time, and they could reduce the consumption of energy down to 45 kilowatt-hour per kilo, which is a fantastic improvement. So this is one innovation. Another innovation to which many Swiss companies took played a decisive role was the introduction of not only cutting the silicon with multi-wire, but it was also to transition from cutting with the wire and with some silicon carbide particles, and to really start to use a wire coated with small diamonds. And thanks to that, in these wires, you really cut 6,000 wafers at the same time. And with the diamond coated wires, people have been able to reduce the losses of material from around 200 micrometer down to 65 micrometer. That means by transitioning to this diamond wire cutting, suddenly you get more or less 60 or 70% wafer more. So less energy for your silicon, and you get many more wafers per kilo of silicon. And then you have all other kind of innovations, such as increasing the number of bus bars at the front of the solar cell. This allows to save on silver cost. This allows to gain some efficiency in the module. If you put all that together, improve processes, improve efficiency, improve sewing, you see that now we went from around 17 grams of silicon per watt down to 3.5 grams per watt, and with much less energy in the gram per watt. And if you have a look at all that for every part of the process chain, in the end, you find that to make a modern crystalline silicon module, you will need something such as 0.5 to 0.8 kilowatt-hour per watt of module. And your 1 watt will give you in Switzerland 30 kilowatt-hours over the lifetime. So you put 0.5 kilowatt-hour and you get at the end 30. So it's roughly, let's say, half a year at the module level to recover your energy. So this is the energy payback time. And now if you have a look at the CO2 content, you need to know which kind of electricity you used to make your module. And if it's a Swiss clean electricity, or if it is a China carbonized electricity. And of course, here, the value will change a lot. But you can also calculate that depending on the sources of your electricity, you are per kilowatt hour of solar electricity produced at an equivalent CO2 at the module level between 7 and 30 grams. 7 would be the best case of everything made in Europe, and 30 is the worst case of everything made with coal in China. And this 30 gram has to be compared to 400 grams for coal power plant, or 1 kilo, 400 grams for gas power plant, or 1 kilo for a coal power plant. Okay, so now let's assume I take a Q-cell module, which is a good module made with some good practice. Let's take 300 grams, which is kind of soon average value for this emission. And now I can have a look at my planet here, and I can have a look at what I need to do if I want to stay within this 2-degree scenario. And within the 2-degree scenario, we can still emit 1,000 tons of CO2, gigaton of CO2. We emit currently around 40 gigaton per year. So for the 1.5-degree scenario, you forget you just have 6 years left, so we will never reach that. But the 2-degree scenario is possible. So we could still emit 1,000 tons of CO2. And then I can do the calculation with the current good but not best practice. Good practice for photovoltaics. So I told you maybe 30 terawatt of photovoltaics. So I need to keep 9 gigaton of CO2 for making my solar panel. I take the wind. I need 10 terawatt of wind. Wind has better energy balance than photovoltaics because it produces more kilowatt hour per watt. So I need 5 gigaton for the wind turbines. And then I still need my batteries. I took 4 billion battery systems, 4 billion cars, quite a lot. Also takes the real value, not the fake value propagated by the oil industry, which doesn't like the electric cars for good reasons. And then I come to 12 gigaton of CO2. So this is everything you can do now, not even with everything clean, just now. And if I take all that, this is 5 gigaton of CO2 emission. I remind you, we emit around 40 gigaton per year, and we still have 1,000 gigatons. So basically what I'm telling you is that with current good practice, we need to keep 2.5% of our emission to make the energy transition. It's not too much. So it shows that the system per se would work. And of course, the more you start to make the transition, the more you start to improve these numbers, because once you're producing your electricity, managing it with only renewable sources, then everything is improved. So it's a system that works by itself. And it needs to be started. So if you want to go further, let's continue just with the technology because I like it very much. If you want to go to make even better solar cell, and why do you want to make better solar cell? Because, well, if you can increase the efficiency, you reduce all the system costs always. You know, if you double your efficiency, all the area-related system costs go down by a factor 2. And this is quite often a large part. So you would like to go to 30% solar cell. But silicon has a theoretical limit, material limit at 29%. So the only way to go higher than 30% is to combine materials. You could do that as you have in the solar cell for space, but they are quite expensive. You could make concentration, and there is one fantastic startup called Insolite with very innovative product where you focus the light with micro-tracking system. It is one option. But the very big thing now is the new material called perovskite. Well, perovskite is a crystal structure, but some people found out that you have some specific crystal structure based on organic, inorganic compounds that were actually quasi-ideal semiconductors. And here you can start to make really fancy solar cells. And here I show you one of the solar cells where we've been very active in Neuchâtel. It is a crystalline silicon solar cell, an heterojunction. And on top of that, we add a few layers, a perovskite that absorbs the blue light or the green light. So you need some interfacial layers, but you can basically make a kind of industrial process out of that. And we've been working quite hard at making this kind of tandem solar cell, perovskite on silicon, and it has a potential for reaching over 30% efficiency. The process is still a little complex. The stability is not yet at the level where it should be for a product that should last 30 years, but there are good improvements. At least in the lab, now we have some quite interesting results where we could demonstrate efficiencies over 28% with these small solar cells based on perovskite silicon, and I'm convinced that within 1 year or less, we'll reach the 30% mark for laboratory samples, not yet for products. So now in the last 5 minutes, I will just show you a few more of the things that you can do with photovoltaics, because now I have spoken mostly about technology, solar modules, but now you can do so many things with solar that you can go beyond simply the cheapest. You can also do sometimes the nicest or the most useful. And the first example, and I have it here with me, is using the old technology such as thin-film silicon to make fantastic products. So you can see on my wrist, I have a watch made by a Swiss company. I will not cite the name here. And this watch is connected. You can use a smartphone. It has altitude. It has a touch screen, so it's fantastic. And you never need to recharge it because it has one of the best solar cells in the world, which works particularly well under inline door. So it is based on thin-film silicon, and it's commercialized by, of course, Tissot. So this is one application. And here the team at CSEM, which emerged from PV Lab quite a long time ago now, is really ensuring there's a pilot production, or even the production of such diodes. Then you can use the low-cost solar cell to make special products. And we've pushed quite far the development of special packaging solutions. So in Neuchâtel, we can formulate polymers, we can extrude polymers to then make all kind of very special laminates. And we use these laminates for a lot of application. And of course, solar boards, this is a solar board of Raphaël Dangean, but then we went for many more specific, say, solutions for really board that needs to go into Arctic regions or very hot regions. And these are solar panels with very high efficiency, with special polymers on which we can jump, walk. This is a kayak in the Antarctic. This is a Swiss solar boat, a nice student project where EPFL CSM was involved for manufacturing these lightweight and high performance modules. These are stratospheric solar planes. This is a plane that should go in the stratosphere. This was the first jump from a solar plane, parachute jumping by Raphaël Dangean. And this plane here should go to the stratosphere. So we're working very hard to further improving the solar panels. And these are very lightweight crystalline panels here, less than 700 grams per square meter. These are here balloons of the French National Space Center. They send a lot of balloons in the stratosphere. And on the balloons here, you can see a lot of small, lightweight, carbon-based support with high-efficiency solar cells. And all these things are assembled and made in small series production at CSCM. You can do many more things. This is a fantastic product of the society DHP in Switzerland. And you see here, these are systems you can unfold on top of, for instance, sewage station, parking lot, tennis court. So you can also use spaces which are not only on the buildings. So a lot of possibilities for deploying photovoltaics. But of course, one that I like quite a lot is we are in Switzerland, we are a beautiful country, and people are very sensitive to aesthetics. So people don't like it like that. People rather prefer to have it discreet. and this explains why we have a lot of companies in Switzerland that try to develop nicer and special photovoltaic products, where you don't need to pay the least, but it needs to be nice. And in Europe, you also have quite a lot of companies. And we are involved in many developments with the EPFL PV Lab and the CSCM PV Center. But very clearly, there is also a good potential, of course, on the roofs, even on the facade. In Switzerland, you could produce around 1/4 of today's electricity demand with the solar facades, which in addition produce as well in winter as in summertime. So a fantastic possibilities. Of course, you have a fight between the architects, which want to make fantastic, beautiful projects that sometimes really too expensive and too unique, and the engineers who wants to see photovoltaics everywhere. And I'm having a lot of arguments with architects and with engineers to try to find the best way to put more photovoltaics everywhere into the building. But certainly what has come up in the last years is something that will help develop this market. And of course, you have first this simple roof integration of companies such as Trias Solar Plus, which make beautiful mega-slate system. You also have from Schweitzer, from Eternit, a nice solution, but the one of Trias is manufactured in Thun, in production lines, really making every day thousands of square meters of solar modules. And what has changed in the last years is that based on the demands of the engineers, we've really thought, how could we make things completely different? And we came with what we call the transformative photovoltaic technologies, which was to say we have crystalline silicon, it's becoming so cheap, we could actually sacrifice part of the light, we could reflect it, we could use the infrared and give fantastic visual appearance. And we could really develop the first white photovoltaic modules. So I tried to get some support from the US President Trump when I was there last trip. So he didn't like my proposal. So then I came back and then we worked very hard with a startup of CSM called Solar Access. And we've made now quite a few projects and we have a technology available for making at quite low cost white photovoltaic modules. You can see that here. And one of the first fully white house. So this is the first thing. If you can do white, you can do a lot of other things. And we had made also this project with a different technology in Switzerland. It's on an old farmhouse. It was the first terracotta roof. So these are all crystalline silicon modules. And you can see this beautiful renovation. Which shows that there is actually no limitation in what you can do. So this project has made a lot of small brothers. You can see here private people equipping their house, the wine caves in Neuchâtel, the Moulin Bayrel, and a more recent example with technology of Solar Access, which is an old post in Zurich, fully covered with this beautiful terracotta. And I like this kind of project. I think it's really for the city fantastic, but I can also tell you that there are some organizations of the patrimoine in Zurich, they have attacked this building because they think you should not change the roof of the buildings. So it's not going to be easy to make the transition. I wonder how people want to do that. But basically, the technologies are available. And if you can do all that, you can do that either larger or smaller. You can see here a beautiful roof, which contains a lot of small modules, all interconnected with, in addition, small inverters or power optimizers. And here you have solar on the four roofs or the full roofs and even on the edges. So this is a very special high haute couture photovoltaic project. And I will not tell you whose roof this is. But you can do a lot of such roofs, and we have the society Freesense developing beautiful solutions where you really are having, such as here, this 3 cells solar module. This is the same here with sandblasting. So you can start to have beautiful possibilities. And this is the last project that John Morello did. It's completely crazy. These are modules where each tile has 3 colors. And this is really a photovoltaic module here.
It's art.
This is art.
Yeah.
Okay, so it's of course a little more expensive, but if you can do that, although we showed a few years ago that you can also combine photovoltaics with high quality images, and we've done a lot of beautiful projects sponsored by the local bank. These were all photovoltaics, 2 by 2 square meter modules, and you will see more and more of these photovoltaic images at the lake of Neuchâtel. You can see this is all photovoltaic and it produces electricity. We stay here for years. Exhibition all around the world. Private people buying photovoltaic pictures and generating kilowatt hours. This is the end of a garden here. See? You can make a few thousand kilowatt hours per year with these beautiful integrated walls. And there was even a beautiful exhibition that I hope that many of the EPFL students could visit at the EPFL pavilion. Okay, so with that, I'm coming at the end of my presentation. I hope I could show you why photovoltaics is really something that will help for world decarbonization. It is necessary. There are not so much other option. We need much more of that. We need to use every available roof. We need to further develop the technology to make them better, cheaper, to facilitate this energy transition. There are local jobs in research, in installation, and in engineering. And of course, every architect, every citizen should take part of this process by actively developing that, promoting, and not blocking. With that, I would like to stop my presentation.
Thank you very much, Professor Ballif. I forgot to mention your your biography. I think I will still say a few words. You're the director of the Photovoltaics and Thin Film Laboratory PV Lab at the IMT in Neuchâtel, which is part of the EPFL since 2009. You graduated as a physicist from the EPFL in 1994 and obtained in the PhD in 1998, working on novel PV materials. You became full professor at the University of Neuchâtel IMT in 2004, taking over the chair of Professor Shah here. Since 2013, you're also the director of the CSEM PV Center, also located in Neuchâtel. You are co-author of 500 journal and technical papers, as well as several patents, and you're elected member of the SATW, member of the Scientific Council of the Swiss AEE, and member of the board of the EPFL Energy Center. In 2016, you received the Becquerel Prize for your contribution to the field of high energy photovoltaics. Thank you very much. Now our last speaker, Professor Arvind Shah. Okay, let me introduce you briefly. You studied in Bombay, London, and Zurich, receiving a PhD in applied physics in 1968 from the Swiss Federal Institute of Technology in Zurich, ETH. Then you worked at the ETH, founding the Center for Electronics Design and Technology at the Indian Institute of Science in Bangalore in 1975. In March 1979, you were appointed professor of electronics at the University of Neuchâtel, and in 1988, you began a concurrent part-time appointment at the Swiss Federal Institute of Technology, EPFL, and you're founder of the Thin Film and Photovoltaics Lab in IMT Neuchâtel, where you were involved in the invention of VHF plasma deposition and the pioneering work with microcrystalline silicon and micromorph tandem solar cells. Since 2000, you have been involved in the successful industrial transfer of technology, negotiating major licensing agreements both to startup and established companies. In 2007, you received the Becquerel Prize for your groundbreaking work on silicon thin film solar cells. Thank you.
Thank you very much for the introduction. Yeah, I have a very brief presentation on the status of PV. You could perhaps go to the first slide.
Yes.
PV accounts today, and I'm talking of 2020, for the generation of 900 terawatt hours per year. And this compares with some 27,000 terawatt hours per year total electric production. So PV is just about 3% today of electricity. Next slide, please. Now, in order to have an impact on climate change, which was my successor, Professor Ballif, was talking about, we should provide, through PV, 50% of all electricity. And that would be 50% of 50,000 terawatt hours per year by 2050. I have assumed a 2% increase in electricity per year. It's very clear that the consumption of electricity will increase, maybe by more than 2%, because electric cars are coming up, heat pumps, there's industrial development in emerging countries. So we must increase PV current from present 900 terawatt hours per year to something like 25,000. That's a factor of 30. Now, this means an increase of 12% per year. However, we should note that during the past 2 decades, PV grew at a rate of 30% per year. So this 12% per year we need is really modest. Maybe the next slide. So this is possible. PV cell production should become fully ecological. It's not the case in China as of now, because their coal-fired plants are used for electricity. The storage problem should be solved. Personally, I do not think it should be solved based mainly on lithium-ion batteries, because that will create its own ecological problems and material problems. There are degradation issues that have to be fully solved in the solar cells, and many people are working on that. And what we absolutely need is active political support, which we are not really getting as yet. Next slide, please. So I take this occasion to make a bit of publicity for a book I recently edited. unfortunately, it's rather expensive, so you better ask your library to buy it for you. This book, Solar Cells and Modules, and all the images now will be from our book. Next slide, please. One of the very important issues in designing solar systems is the temperature behavior, because modules are sold for standard test conditions. That means 25 degrees centigrade. But they actually have to operate in summer and especially in tropical countries at much higher temperatures. So the temperature coefficient should be low for the cell to be usefully used. And this is shown in the book. This is a new result from a collaboration with a Dutch company, Internal Inspire. We were able to show that as the cell gets better, and as you move to heterojunction and TOPCon cells, which Christophe Ballif mentioned before, the temperature coefficient also comes down. It also improves. Next one, please. TOPCon cells, this is how they look. TOPCon means tunnel oxide passivation contact. It needs some additional layers, so it's a bit more expensive, but its efficiency is higher. It was invented by the Fraunhofer Institute for Solar Energy in 2013. This is one of the front runners of present crystalline silicon solar cells. Maybe the next slide. Heterojunction cells are also very important. The group here in Neuchâtel is working on that. This heterojunction cell was invented a long time ago by Sanyo, which is now Panasonic's, and it is being used now for factories in Europe by the Meyer Burger company. Maybe the next one. When we go to thin film solar cells, we have CIGS, cadmium telluride, morphosilicon also, which we worked. There are excellent techniques for putting the cells in series without connecting them externally. This is done monolithically. Personally, I think that cadmium telluride cells have a good future also, in addition to crystalline silicon, because they have an ideal band gap and collect the light in a very good way. People for a long time shunned off cadmium telluride because of cadmium, but in the book you can read that this is not a real concern, because cadmium telluride does not disintegrate, even under a fire, into cadmium and telluride. Maybe the next slide. Now, module failures, I will cite here from the PVTech newsletter, May 29, that's maybe Saturday. Solar module failure rates continue to grow. Here are some examples of such module failures. You'll find many more examples in the book. This is a real concern, that the module failure rate must be kept low, and a lot of work is needed here. The next slide, maybe. Floating PV, we have talked about PV on roofs, PV on the land. I think floating PV is an important thing because we can save the space. And this is an example from Japan, from Sierra International. It's on an irrigation reservoir in Japan. Incidentally, the Swiss company Novaton is a pioneer in the field of floating PV. Mark that name, please. Next slide. Okay, we come to the same watch which you already saw, the Tissot watch with an amorphous silicon power supply, and thanks to that, you don't need to replace the battery so often.
But this is the old version.
Yes, I made the photograph in a company some years ago. That's true. So I'll put a new version in. You give me your photo then.
With Bluetooth.
So I come to the last slide. I spent a large part of my professional life trying to understand amorphous silicon. And it was a very difficult task. It's a complicated material. I think I still don't understand it. And maybe nobody understands it. So, thank you very much for the attention.
Thank you. Thank you to all speakers. I think now we are reaching the end of the presentations, and we are opening for questions and answer. Lucas Riemer is the chairman of the student branch of EPFL. Can you manage questions and answers, or did you see some already on the discussion?
So we already had some questions in the chat, but I'm not sure. Did any presenter already answer any questions? Because we had quite some forth and back, I think.
I think, Lucas, I saw one interesting people saying, should we put solar panels on the north side of buildings, as we can get some blue light nowadays? Any comment on that?
But perhaps not the best idea.
Okay.
I think they're better locations, and we put them first on the other sides.
Yes, okay.
But I can add something. There has been a study by Fraunhofer Institute in Freiburg showing that there is definitely a shift in the orientation of panels. Mm-hmm. In the beginning, they were always placed in the optimal situation, mm-hmm. and now there are more and more panels that are also off. Now nearly half of the panels have another orientation. So that goes to what he said, that the best way is basically to cover all the buildings.
Yes, I think it's important. Thanks to the improvement in the panels and reduced gray energy, you can start to put them even in less favorable position.
Yeah. And this should be promoted.
Yeah.
Michel Villoz?
No, I said that what we do, every time we have a flat roof, we will use dome today to maximize the power. Mm-hmm. So it's really, depending on the client, but we use every roof, mm-hmm. even if they look north. Okay, the efficiency is a bit lower, but if the price of the panel is cheap, who cares?
Okay,
you do a maximum.
Yeah. So, Lucas, do you want to handle other questions?
There was another question about solar panels that can handle blue and red light. What's the status of this?
Well, I think what can handle blue, and this is a mention to this tandem configuration, where you put two solar cells on top of each other. Huh? And in the past, there was with thin film silicon, you could combine amorphous and microcrystalline. It was two materials. And today, with the perovskite, you can imagine of putting either perovskite directly on silicon, or you could even have another kind of module capturing the blue light that you would add on top of the existing crystalline. So you would have a kind of cover. You come with a module that absorbs only the blue and that lets the infrared. And some people are promoting that idea of refurbishing with a module that's very efficient in the blue light, refurbishing the old crystalline modules. In practice, I think it would be not very cost effective, and it would be complicated because of the size. So it's not a very good idea. So the best bet for using these various wavelengths is to really try to have these new materials, perovskite on perovskite, perovskite on silicon. Maybe you have a chance to make this multi-junction and use the solar spectrum better.
Thank you very much.
And I'm sure we will see that coming one day.
Do you have, that was the next question or next part of the question. Do you have any idea about the horizon when that would be available or affordable for private consumer?
For the multi-junction, let's say when you start to put several solar cells, of course, you can already buy now the satellite solar cells. You can buy solar cells up to 22, 23% efficiency, but they are 1,000 times more expensive. But you can buy them for your drone. If you're a rich person, you can make your drone with this space solar cell. For the perovskite on silicon, I think it will enter through niche market at a much lower cost. But I don't like to give really any prediction on the date. So you have some companies such as Oxford PV, very aggressive in Europe. They say that they will start production of perovskite silicon solar cells at the end of the year. No, they displaced it by 1 year. I would rather say it still takes a few years to come to a product that is potentially commercially available. So still a few years, 4 or 5 years. and then to be seen whether it's a big market or whether it's a niche market for, if we don't solve all stability issues, people will not buy them, unless it is for applications such as drones, where you don't need to survive 25 years under the sun. So I'm still careful about what you can do with that.
Okay, thank you very much. I think that were all the questions from the chat. Do we have any other questions?
Yeah, how is it? People should raise hands, is it right?
Raise hands, unmute, write it in the chat.
Okay. No questions? Okay. So I'm sure you covered many things. So may I suggest to all participants to turn on the video to make a group picture.
That's nice.
Yeah, screen capture, yeah. You can see here.
Yeah. Ah, yeah.
Oh, and here, yeah.
It's coming up, yes.
Very nice. I think we had around 38 people at one time.
That's good.
So that's quite pleasant. Okay. Thank you very much. And to conclude, Hugo, do you want to say a few words of conclusion of this?
Well, can I speak from here?
Yes. Yeah. The camera will move to you.
Well, I just wanted to give a little historical glimpse. As you heard, the two speakers that we had here, they got the Becquerel Prize. The Becquerel Prize is because of a French physicist by the name of Becquerel, but not the one who discovered radioactivity. It was the father. And that goes back to 1837, I guess, when this physicist Becquerel discovered that light could generate electricity in an electrochemical cell. It was just 40 years after Volta discovered the voltaic cell. So it took a long time. It was a curiosity. And then it was actually at Bell Labs when the people started studying semiconductors. The idea came up to use silicon diodes for making solar cells. That was actually in the 50s, 1950s. At that time, the cells were still a curiosity, and the boost that came for using solar cell then was the space. When people started putting up satellites, there was a need of having an energy source, and it came, the best energy source that they could come up was solar cells. And then from that point on, let's say 70s, 80s, solar cells started becoming something, let's say, realistic. And after that, basically, there has been a big development worldwide. And we have got now to the point where solar cell energy is the cheapest one, as it has been pointed out. But I still would like to stress one thing. Solar cell, as the name says, is linked to the light of the sunshine. So it is only useful generated during the day. On the other side, if you look at wind generators, it turns out that very often wind are very strong during the night. So there is a basic symbiosis between photovoltaics and windmills. And this, I think, is something that should be stressed very much now when we want to master the conversion to sustainable energy, that we should push both. Of course, for instance, in Switzerland, it's very difficult with the wind because there is a lot of a lot of opposition for many reasons. In other countries, like in Norway or in England, the wind is going on very quickly. So the real problem that we have now, it's no longer having to install the wind or the solar plants, but to make sure that they are well connected together, so that we can always get, for instance, a lot of energy from Scandinavia when there is there, and take it down here, and then on the other side we can absorb the energy in the south and transport it to the north. And this, I think, is a real challenge. It's a system challenge. Okay, I think with that, I made my point.
Thank you very much. So I think we can conclude, and I think we are even on time, which is quite nice, as planned. Thank you very much for all the attendance, and thank you to the speakers. Bye-bye. Bye-bye.
Bye-bye.
Bye.
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 Bye.